This is the seventh and final part of Lecture 8 of Elect 5300. In this final section, I'd just like to discuss the exponential family of distributions. This family includes many of the distributions that we have discussed in this class. I'll show you two of them that lie in this distribution. But the important thing about this exponential family of distributions is that all members of this family have a conjugate prior. And so if there's a distribution that's in this family, then we can perform Bayesian estimation using the conjugate prior. So the form of the exponential distribution family of distributions, they all have this form that's shown right here. The important parameters are these parameters eta here. These are the parameters that determine the shape of the distribution. And so by adjusting this, we change the shape of the distribution. But the kind of natural functional form is determined by these functions u, h, and this final function g here is really just a normalizer. What it does is it just adjusts the scaling factor here so that when I integrate the rest of this function over x, just make sure that this thing will integrate to 1, and of course the integral of this thing will depend on the eta. So the key things you really have to worry about then are this h and the u and the parameters eta. So let's take a look at two distributions that fall in this class. One of them is discrete, the other one is continuous. So that's one of the interesting things about this distribution here, is that it can be used to handle both discrete and continuous random variables. So the first one we'll look at is the Bernoulli distribution, and we saw before the Bernoulli distribution can be written in this form here. And so in order to get it in the exponential family, the form, what we'll have to do is kind of group the terms in x. And so in order to do that, what we'll do is we'll take mu to the x, and then we'll just take 1 minus mu to the 1, right, and then 1 minus mu to the minus x. And so when we do that, we get 1 minus mu outside here, and then we get mu to the x and 1 over mu to the x, so that gives us this. And then we can take the exponential of the log. That really doesn't do anything, but when I take log of this to the x, it's the same as x times log of that. And so this is the general form of the exponential family of distributions, and so all I have to do is just kind of match terms between here and here. So the first thing I'll do is I'll match this term and this term, so you can see here that u of x, this function here, is just simply x. Right? The parameter eta is just log of mu divided by 1 minus mu. H of x here doesn't appear here, so we just have h of x is equal to 1. And g of eta, the normalizing term, is just this thing here, right? And so this is in terms of mu, right? So if I know that eta is equal to log of mu divided by 1 minus mu, then I can invert this thing to get mu, right? And it turns out if I do that, I get mu is equal to 1 divided by 1 plus the exponential of minus eta. And so g of eta then is just the same as 1 minus mu, and so I just take 1 minus this, and I get e to the minus eta divided by 1 plus e to the minus eta. So you can see here all of these terms can be matched exactly into this distribution, and so therefore the Bernoulli distribution is a member of the exponential class. So that was a discrete distribution. Now we'll look at a continuous distribution, which is the Gaussian distribution. So this is the regular form of the Gaussian distribution that we see here. In order to get it into the form of the exponential distribution, I'm going to first expand the quadratic inside here, so I get minus x squared divided by 2 sigma squared, minus 2 times x times mu, and the minus here cancel out, so I get a plus. The 2 and the 2 on the bottom cancel out, so I get mu x divided by sigma squared, and then I get a minus mu squared divided by 2 sigma squared. Then what I can do is I can leave only the terms that have x inside the exponential. So I'll pull this term out into its own exponential, so I get 1 divided by the square root of 2 pi sigma squared exp of this term here that I pulled out, and exp of this term that depends on x squared, and this term that depends on x. And so now again, this is the general form of the exponential family of distributions. And here I have to use the fact that u can be a vector function because I have x and x squared. Right? So I'll have the vector here u be x squared and x, and the parameter vector is just going to be the things that multiply, the coefficients that multiply x squared, which is just minus 1 over 2 sigma squared, and the thing that multiplies x, which is just mu divided by sigma squared. And so those are my two parameters, eta 1 and eta 2, that determine the parameters of the distribution. And so you can see that there's a relationship here between the mean and the variance, which usually we have to estimate, and these two parameters, eta 1 and eta 2. So given eta 1 and eta 2, I can find the mean and variance, and vice versa. So if I look, I've taken care of this term inside the exponential. That's really the most important thing. I look for any terms outside the exponential that depend on x. There are none, so I just say h of x is equal to 1, and then I just have this scaling term here that makes sure that when I integrate this thing from minus infinity to infinity over x, I get 1. So the scaling term is given by that. That's that g of eta, which has this form here. And by substituting in the value of eta 1 into this, you can verify that these two expressions are the same. So I can take this, which depends on mu and sigma squared, and express it in terms of eta 1 and eta 2. So that's my g of eta, which is the normalizer. So we've seen then two distributions, a discrete distribution and a continuous distribution, that can both be expressed as special cases of these exponential family of distributions. So finally, I'd just like to show you that the exponential family has a conjugate prior. The conjugate prior has this form that's shown here. So remember, the parameters of the exponential family are those eta parameters. So if we go back, you can see the eta controls the mean and the variance in the Gaussian case, or the eta determines the mu parameter, the probability of heads, in the Bernoulli case. So that's where the eta vector is where the parameters lie, and so we need to find a distribution over those eta parameters that depend on some hyperparameters psi and nu. And the conjugate prior has a form that looks very similar to that which we saw in the exponential family. It's an exponential of something times eta, right, and g of eta. And this thing here, this k function here, is again just a normalizer. So we really don't have to worry about this k term. It's just there to make sure that when I integrate this thing over eta, I get 1. So we can verify that this is a conjugate prior just by multiplying by the likelihood, right? So the likelihood is this, where I have taken into account that I have n pieces of data, so I've multiplied the likelihood. G of eta here doesn't depend on the data, so I just raise it to the nth power, and multiplying the exponentials here is the same as taking the exponential of the sum inside here. And so when I multiply this times this, you can see that I just get a normalizer over here and a normalizer over here. These things really don't come into play, and so really the important action takes place with the eta. So here I get g to the eta to the n plus nu, times the exponential of nu eta transpose times xi, nu eta transpose times xi, times nu times the summation of mu uxk. And so here you can see that the posterior distribution, after I take into account n pieces of data, is obtained by taking this new hyperparameter here and augmenting it by n. So this hyperparameter mu corresponds to kind of the number of effective observations in the prior. And we can see here this is the sum of all the observations, or actually the nonlinear functions of the observations, and the xi here is just multiplied by the number of observations here. So the xi here is kind of like the value of the nonlinear functions of the observations in the prior. So I'm just going to take those and update it by the prior, the data, the nonlinear functions of the data that I have observed, and that's going to be the way that I update the hyperparameters. And so this is a little bit complicated, but the important thing to realize is that any member of the exponential family has conjugate prior, and we can do Bayesian estimation. Okay, so that concludes lecture 8.